Alright everybody, welcome to the Metpy tutorial, and for those of you who may not have heard already, due to version control from Anaconda, this has been a bit of a headache for a number of students to install correctly, so we are now moving this assignment to an extra credit form of an assignment. So this is not a mandatory assignment, just an extra credit now, and I'm just going to run through real quick what happened. So whenever you go to install Metpy and you're under your Geog 3.8 environment, you come over here. The default form of Metpy, the default version is 0.12.0, and this has some incompatibilities with CartoPy. So there's just a brand new version released of this 0.12.2 of Metpy, and the way that you have to install that is manually. So you're going to come over here, you're going to open terminal, and once you're over here, what you need to do is you need to go to, I type in Google Conda install Metpy, and I find the Anaconda Cloud link right here. Click on that, and it has some manual installation text. And the one that you actually need to install is this one right here. So when I actually go ahead and install that, it won't do anything now because I have personally already updated this beforehand, but what it will do is it will update your version from 0.12.0 to 0.12.2. So this is a big help for us because now everything that we need to do will actually be compatible with what we want. So I'm just going to cancel this because I already updated it, but what would happen is it would say, do you want to update these packages? And you just click Y, enter for yes, and go ahead and proceed with that. And now as a result, you can successfully head through the first couple lines here. So this is Metpy, and for those of you who don't know, Metpy is a meteorological data package within Python. It is the highest level package that we'll use thus far, and it's actually built on top of all of the packages that we've covered previously. So NumPy, Matplotlib, Pandas, Xray, and CartoPy, they're all dependencies of Metpy. And that is why with some of these higher level packages, because they are built on so many different dependencies, they have so many different packages that offer a beam in the foundation that one little tweak or version difference can make the entire thing blow up. And that is why we've moved this to an extra credit portion. So, but because our Metpy version is correct and it now matches all the other versions of the packages that we already have installed, we can now go ahead and run through this. And so yep, there we go. Okay, for some reason that did not want to run correctly, but we are good to go. We installed all of that just as it should have. And what we're going to do is we're going to run through this a little bit faster than we would normally just because it's extra credit, but I will run through it. And what we want to do here is we're going to just run to and navigate to the file that we did for the last assignment, which was the treecove.nc, so tree cover percentage of the world. And for me, that's in my downloads, and then geog master datasets treecove.nc. All right, so let's run this, make sure everything works correctly, and I forgot to highlight the D. There we go. Okay, so just tree cover data, and we have dimensions of latitude and longitude. So there we have tree cover as our variable, latitude, longitude as our dimensions, just like we did before. But what we're going to do now is a little bit different. So we are going to use Metpy parse _CF. So this is where the higher level nature of this package comes into play. So CF is a convention format, and it's a universally standardized convention format. So we have standard units, they're called CF units. such as Kelvin and mostly metric units like that. And so these are just very standard agreed upon units and that sort of thing. But this also does a little bit more than units. It also will give us some more information regarding this data frame. So we just have data as our X-ray data set right here. But watch what happens when we run Metpy Parse CF on the data set on the variable Trico. So Trico is my variable right there. So that is the variable, and then data right there is going to be the data set that I call. So I run that line, and we just get a little extra note here that just says that it found the latitude and longitude values, so it's assuming latitude, longitude for the projection grid mapping variable because there is no projection metadata. So it's assuming a projection. So now when I run tree data, notice that it added in a CRS, or a projection. CRS, remember, stands for Coordinate Reference System. So remember, we're dealing with a bunch of projections in geospatial data, and CRS is a method for defining that. And so what Parse CF is going to do is it's going to give us our units, and in this case, our units are percentage, and it didn't really know what to put down for that, so just units of 1, which is just a place filler essentially, gave us a name, and just some new, it automatically assumed some attributes. So it got rid of some of this metadata up here, but that's okay because we don't need that. We just wanted to do that for this particular variable. Now what we can do is we can print out the projection. So I have my proj, which is just going to be equal to the CartoPy CRS. So this CRS right here can be queried from this tree data array using .metpy.crs. So now when I print out proj, tells me that I'm in plate carry. That is the assumed projection. It assumes that because it's not defined as a variable or an attribute, but in this case it's correct. We are in latitude and longitude. We are in EPSG 4326, which is just a standard pretending the world is flat projection. It's not pretending the world is flat, but it's visualizing it as if it's just 2 dimensions as opposed to 3-dimensional oblate spheroid. Now what we can do is we can just take that and take our tree data set, and we can just plot it like so. So I'm going to go to my plots, and there we go. So we were able to do that really quickly right there, and we can even take it a step further and we can reproject this very quickly. And so let's say we wanted to visualize this data set as a Robinson projection. We have our proj defined, and I did that over here in the console. Let me put that over here in the script so that it's saved. So now we know our proj, which is plate carry, and what I can do now that I've extracted that data is when I go to plot the data, I can add in a little thing called transform. So transform is the projection that we're transforming the data from. So it's the original projection. And because we need to transform it because we set our new axes projection to CCRS Robinson. Remember that CartoPy CRS is imported as CCRS. So we want Robinson projection. We're saying, okay, let's initialize a figure. Let's put axes on that figure, and we're going to recognize this axes as Robinson projection. Just run that, and boom, now we have a new representation of this particular data set, and we're going to represent it as Robinson projection as opposed to just plate carry. So transform equals proj tells Python what the projection of the data came in. So now we're going to dive into meteorological contour plots. And what you really need to know about contour plots is we're just trying to map out different regions of a 2-dimensional surface. in this particular case, what we're going to be looking at up here is we're going to be looking at heights of a particular pressure level. So what this is it's a pressure level. So it changes with different meteorological conditions, and we know that storms come in the form of low pressure. Sunny days are typically found under high pressure. So it's all about ascending or descending air parcels, and we have these parcels are associated with different pressures. And what we see is that these pressure levels, the lower the pressure, the closer those contours are to the ground. So what we're doing is we're just identifying different heights of atmospheric pressure. So we're in Newark, Delaware, we're pretty close to sea level pressure. We are not that far off of the ground. Whereas if you go to Colorado Rockies and you're up, 10 to 14,000 feet, you could be, even though you're that high up, your pressure level is going to be far different because of that. And you might only be experiencing, 66% of the pressure, roughly two-thirds of the pressure that you might experience at sea level. So the air gets thinner and the pressure decreases. So let's go ahead and let's read in this data set. So we're loading in GFS 2010-1026 at 1200 NC. And I need to copy up my path up here. Copy that, and let's go ahead and run that. And so there's GFS. And so GFS stands for Global Forecast System. It is the world. It's a world scope. It's a weather forecast model. It's a weather forecast model that covers the entire world. Even though it's managed here in the USA, we are using this as a weather forecasting tool for the entire world. So this is a forecast. So GFS stands for Global Forecast System Weather Model, and we have some different things that go on in here. And what we see is that we have some more dimensions than usual. We not only do we have lat, lon, and time, we also have isobaric levels. And isobaric are lines of constant pressure. So we want to know where a line of constant pressure is. And we know we're going to have concentric rings around a low pressure and a high pressure. So we know we have time values, and we have these different isobaric heights, these lines of constant pressure right here. And so we can actually dive in. Let's just explore this a little bit more. Let's extract the isobaric 3 data right here. Notice we have units of pascals, which is a pressure unit. We have the long name is isobaric surface. It's lines of, or it's just constant pressure surface. So here we go. Isobars, lines of constant pressure. A line drawn on a weather map connecting points of equal pressure is called an isobar, and isobars are generated from mean sea level pressure, and stronger winds are associated with larger gradients in pressure. So for those of you who aren't meteorologists, it's okay. We'll still get through this. So now what we're going to do is we're going to grab the projection right here. And so what we're going to do first is, remember, we need to parse this data set, and we need to parse one particular variable from our GFS data set. And we're going to choose geopotential height isobaric. And then we're going to grab the Metpy Cartopy CRS from our getproj. So let's print out our proj, plate carry. And now what we can do is we can generate a quick plot here of constant pressure lines. So remember, this is just a quick plot, and I'm running through this tutorial a little bit faster than others because This is just an extra credit tutorial. So we have our GFS data set. We have our variable from that data set, geopotential height isobaric. We're telling it we're going to select the height or the levels when isobaric 3 equals 50,000. And we want the time when GFS time value is 0. This is redundant. There's only one time slice anyway. And then we're going to run a contour plot on that. And boom, there we go. So even though this is the GFS, this is the global forecast system, this particular snapshot is only over North America. So now what we can do is we can select the time value and isobaric dimension. So we're just running another, we're not plotting it now, we're just going to actually save these, the height of 500 millibars right down here. And so these are our height of, 500 millibars right there. And we have our lats and lons. Just save those in as an array. Lats, lons, you got it. Now, one thing we're going to do here is these lines are a little bit jagged and we want to smooth those out. And so this is one way to smooth those out. We're going to run a Gaussian filter over these, and all this is doing, this is basically just a statistical smoothing operation. So you have Z500, and what that is, we're just going to smooth some of these variables. We're going to give it a sigma level and an order level, and then what we're going to do is we're going to plot all of this going on right here. And I'm going to plot it, and then we're going to actually talk about this, what's going on. So boom, here's our isobaric lines. We have a couple different things. So we have the regular 500 hectopascal lines, and we also have the smoothed ones. So the smoothed ones are in red. The jagged ones are in black. And if I actually go ahead and if I just save this plot, I might be able to take a look at this in a little bit of a larger light. I'm going to go over here to downloads where I just saved it. And here we go. So we smooth these out, and notice you can see it definitely like right here. Look at how jagged that normally is. We just smooth those out using a Gaussian filter. So we kind of interpolated between, just smoothed it out. So it made it look a little bit nicer, and we have our contour lines. And so basically what meteorologists use these for to identify regions of different winds, areas of low pressure or high pressure. And so what we have here, this is height in meters right here. So you can see that our levels of 500 millibar height, about halfway up the troposphere, are around 5,300 feet, or sorry, 5,300 meters right here, 5,300 meters. And so this is a lower contour, so we know everything in here is going to be somewhere between 5,340 meters and 5,280 meters. So we're decreasing in height right here. And we know that this lower heights is indicative of lower pressure. So we have a lower pressure value right in here, and we can see that based on the heights right there. And the way that we did this, and so this is a little bit confusing, but remember, we just have our Z, we're using our contour function right here. We're running a contour on our axes. Our axes have been given a projection of CCRS Lambert conformal, which means we have to transform the original data set that we have right here. And so these are both redundant right here. And we gave it a color. We gave it these are just contour labels. C label is contour label. And we gave it some levels right here. And so that's where we actually wanted to draw the lines at the contour. So remember our data is, somewhere along the lines, somewhere in between 5,000 meters to 6,000 meters. So we said, okay, we want 5,100 meters to 6,000 meters by 60. And so these are just different, we're just translating physical heights from pressure heights. We're going to add some coastlines, we're going to set our extent, and we also need to add in our transform definition into the set extent, although it doesn't take that particular argument name. We're setting the extent based on normal latitude, longitude lines, so that can work. We're using Carto by C feature, the states, and then we added a fancy title right there. And I run through this line by line right here, so that's how you can actually go ahead and do that. And what we can also do, additionally, we can add things to this plot. So we have these lines of constant pressure. Let's add in some temperature data. So remember, we have temperature isobaric, so we have the temperature at these heights and lines of constant pressure. It's in Kelvin. So we're just going to run our Metpy.Parsing CF on that. And we are going to slice it down a little bit more. So all we're doing is we're just going to slice it down to a smaller view so that it's not taking up the entire image like the isobaric heights are. Then what we're going to do is we're going to print out the max and min temperatures. Okay, what's going on here? We have max and min, or max temp and min temp. And now what we're going to do, same as before, only we're going to add down here contour F. So now what's going to happen? Same plot as before, but we just added in a filled contour of temperature. So everything from here on up is the same. All we did is we just added this right here. We added it to our axes that are defined as AX, and we just used the contour F. We said, okay, X is their longitude values, Y is the latitude values. There's our data. We want to transform it from our proj, which is plate carry, to the projection of the axes, which is Lambert conformal. We want our V min and our V max, which is the max and minimum numbers for the color map that is used. So we only want to plot values within that range. And then we're going to use this color map of BWR, which is blue, white, red. And so there we go. So we have warmer temperatures down here, cooler temperatures up here. And for those meteorologists of you, we know that we have winds travel along the isobars right there. And so we're pulling different air down right here. We're pulling this Canadian air down over here, and that's why we have colder air up here. We're pulling that down because of this low pressure. And over here, we're pulling warmer air from closer to the equator up north along these isobars. That's leading to warmer temperatures. So the last thing that we're going to do is we are going to add in wind barbs, and we're going to do this a little bit of a different way right here. But what we're going to do is, so originally what we were doing is we were parsing using Metpy Parsing CF on individual variables. We don't have to do it that way. We can do it on everything. So now we have this entire data set with Parsing CF values, right, for each different variable. So now we have U component of wind and V component of wind. So what that is X and Y components of wind. And we are going to use metpy.convert units, and we're going to convert that to knots. So it's in meters per second. We want them to be in knots. And why? Because that way we can use wind barbs, which reference values of knots. And so we're going to select, just like we did before, we're going to select our height level. We're going to select our time. Now we have U winds. There's our values, and then these are our, we just have 2 dimensions now right up here. These are our wind values, and we converted them to knots and before. And now we just add in, right below the temperature, we add in a wind slice, and we add barbs to that, and then we can save that figure. Copy all that. It's a lot going on here. And so everything's the same as the last plot through here, and then we're just adding barbs. And it works the same way the contour plots do. So we have our particular lat and lon values. We added a length. We wanted our wind barbs to be 6.5. It's our length, 6.5 is our value. The pivot is going to be middle, and these are just specific to the wind barbs. We can transform that projection. So there's a lot going on here, but it leads us to a super helpful image that just tells us so much. It tells us which way the wind is blowing at this level, and we can see that we have low pressure here. Once again, tells us the temperature, tells us the constant lines of constant pressure. There's a lot of information to come out through this plot. So that's Metpy. There's a lot of other examples online about the power of Metpy, the different things that it can do. This is just one example that I use, just a simple one over that just shows off the different plotting mechanisms that Metpy has to offer. There's a lot you can do with this. And for those of you who want to tackle this extra credit now, what we're going to do is we're going to use a data set that is actually pre-installed with this package called PyTest. And PyTest is, you have to install it manually like this with conda install PyTest. And there's just some test data sets involved there. And what we're going to be doing is we're going to plot Hurricane Irma. And we're going to give it a timestamp. Or you can select any timestamp you want. And we want to choose the isobaric level of 8,500 geopotential meters, instead of 50,000 like we did above up here. So this is how you want to start off before you get going. And I'm going to run this. And so it's going to download Irma GFS example.nc from get test data. Now we have data, and it looks a lot similar to what we just did already, only now what we can do is just like up above where we selected, you know, the isobaric 3 of 50,000. We're going to now select the isobaric level of 85,000 right here. And then you just want to focus it over Irma. So all that means is, you know, we set our extents up here to the United States. So you'll just have to figure out where Irma is and then try and focus it in a little bit. It should be down over here somewhere. So you just have to focus that in and trim down your extents. And yeah, just a reminder, this is just an extra credit portion. This can be really helpful, especially if you deal with geospatial data sets that are changing with projections and you need something to keep an eye on the projection levels. It just, you know, tells you what projection is what and can handle that information. It's just incredible for plotting meteorological data as well, and there's even more that you can dive into. But again, this is just extra credit. This is not mandatory.